Thank you for the introduction. Hello, everyone. And I'm Marco Maurizi from 10U. And today I'm going to show you this preliminary work together with Professor Chao and Filippo Berto. So I'm going to show you this work basically on exploring the property space, as the chairman said, of lattice materials using by inspiration machine learning. And now I'm going to show you why we perform this research. So first of all, most of you, I think, know what lattices are. And so you know that additive manufacturing, so the recent advances had allowed us to fabricate lattice materials, which are basically also called cellular structures at different scales, as you can see here, from the macro to the nanoscale. And they show unique combinations of mechanical properties like high stiffness, strength to weight ratio. So we can obtain basically stiff materials, but and a weight and light at the same time. So here I'm comparing by inspiration versus machine learning, since usually what is done is to take inspiration from biological systems. Here, for example, you see diatoms here, which are kind of algae and bones or glass sponges. And here we see the correspective by-inspired design. And so recently we have a huge increase so thanks to the huge increase of powerful capabilities of machine learning, we can basically enlarge the design space and find really interesting properties compared to by-inspired design. However, what we can see from machine learning algorithms is that so we have really large design spaces, but most of the designs are not so useful. Indeed, as you know, most of the designs are so the best designs usually are symmetric, and they have symmetries, as you can see here from the sponge design. And that's the reason. So what we wanted to do is to combine the by inspiration, the machine learning. And here we took inspiration from the glass sponge I showed before, and from a recent paper where the authors, inspired by these deep sea glass sponges, design a unit cell with a high buckling strength. And from the observation that this design has a cubic symmetry, as you can see here, P4M crystallographic symmetry, we generalized the design to have some nodes, which are the green, the red nodes on the boundary and the green nodes inside. And then you isolate this triangle of cubic symmetry, and then you obtain the material and generalize the design. So we have two possible design strategies. One of them is
just a minute, because there are problems. There is a noise, so we are not able to hear you. Try now. It should
hear me?
No, now yes. Now it should be okay. Should be fine.
Okay. Sorry.
Okay, you can go on.
Yeah. So as I said, we have two possible design strategies. The first one is we fix the boundary nodes, which are the red nodes, and we could change the connectivity, which is how many beams are connected to each node, or and which nodes are connected to each other. And the other option is we fix the connectivity, and we move the position of the nodes inside here on the boundaries, or inside by moving the green nodes. And then we have what we use. So here we have two possibilities, which are the first one on the right. We can use a classical deep neural network, even if there is no time here to explain how it works. And then we can use on the left. You can see here a graph neural network, which basically has as inputs a graph, which is a compound of nodes and connected to to each other by edges, which are the beams in this case for the lattice material, and it outputs another graph. And then using another fully connected layer, you can output also scalar values, which can be, for example, which could represent mechanical properties. So the simplest case that we applied our approach is we have one node per edge. So we have one red node per boundary node per edge with z equal 4, where z is the connectivity, which is the number of beams connected to each node in average, and it's equal 4 if you generate the unit cell by reflecting the triangle and then tessellating the space. So z equal 4. Here are some examples, and then we applied periodic boundary conditions to the single unit cell with together with different loading directions. We perform we apply uniaxial tension strain at different loading directions. This is an example in one unit cell, and you can see that, for example, here in this plot, we obtain different huge range for the Poisson's ratio ranging from minus 0.85 to 0.6. And then we basically applied, we wanted to predict the Poisson's ratio in this case using graph neural networks, which is the first time that someone is performing this task. And as you can see, we can obtain with really high accuracy the prediction of the Poisson's ratio, generating a database of 1,000 random geometries, 1,000 random unit cells. And then the other case is the variations on the spongy spire case. So starting from the spongy spire design, we take the smallest, the basic element, which is the triangle. We enumerate each node, and we enumerate each beam. And what we do is we can moving the boundary nodes. So moving randomly the boundary nodes on the edges of the triangle and keeping the interior nodes constant, we can obtain different unit cells. And we put the constraint of constant relative density, so the volume fraction, and constant slenderness ratio in each beam, which is the ratio between the thickness and the length of each beam. And then with some strategy we generated random geometries moving the boundary nodes, the red nodes. So some results here. What we did, we wanted to predict the post-buckling strength. So we perform post-buckling analysis, first performing an eigenvalue linear analysis, and then apply the first mode shape to the single unit cells, and then performing the post-buckling analysis, non-linear one, and generating a data set, as I said, of 1,000 geometries with an incompressible hyperelastic material. We predicted the normalized stiffness of these structures and the buckling strength. As you can see from the coefficient determination, comparing the actual and the predicted value, the normalized stiffness is much easier to predict, of course, compared to the buckling strength, which is computed in the which is predicted from the post-buckling analysis. So therefore, so some improvements are needed, and some further research is needed to investigate if we can reach higher accuracies for the buckling strength prediction. Thanks for your attention. So if you have questions, or if you have other questions, you can contact me by email or Google my name.